Recording. We're on. Okay, we are going to finish up lesson 8 in our Polygons and Geometry book. This is part 2 of the Polygons lesson. And let's start by talking about diagonals. So, grab my pen. And here we go. First of all, let's define what a diagonal is. A diagonal is a line connecting two non-consecutive vertices. Our phones should be away and we should be doing the notes. So a line connecting two non-consecutive vertices of a polygon. So here's look at the picture of the square. Right? Obviously, this vertex is consecutive to that vertex. That means in a row. So they already have a line connecting them. That's the actual line of the square. But notice this vertex and this vertex are not next to each other. So the line that connects them is called a diagonal. And a square, like every quadrilateral, has two diagonals. Cool. How many diagonals do other shapes have? Check out the octagon. Octagon's got 20 diagonals. Let's try something a little easier than the octagon. Let's jump down. Don't worry, I'll go back to that formula in a minute. Let's try drawing the diagonals in a pentagon. So how would we do this? Let's do this systematically and count them as we go. I'll start at this corner, and that means, okay, again, I don't have to draw to this corner, but I have to connect this corner to this corner. So this is a diagonal. So there's one diagonal. And then I'll draw to this corner. There we go. Two diagonals. I'm making a tally chart. That's it, right? There's nothing else I can do from this corner. So I drew two diagonals from that corner. We'll keep track that way. That might be smarter than the tally chart. Okay, now let's go to this corner. Well, once again, I can draw one diagonal to here and one diagonal to here. So two again. Hey, maybe all the corners I draw two diagonals. Well, actually, no, that's not going to work. Because take a look at the next one. I already have a line connecting this one. So I really only need one more. One more from there to there. Sorry for the pentagram. It's like, oh no, what'd you do in math today? Well, we were talking about shapes, then we accidentally summoned a demon. Oh no! I'm not superstitious at all, so that's just a shape to me. But anyway, 2, 2, and is that it? Yeah, because if I go to this corner, well, I already got the diagonal to here and to here, so I guess it's really kind of 0 and 0. Oh, interesting. Let's see if we could do the same thing for that octagon. Now, the octagon here, the notes kind of spoiled our fun and did it for us, but let's say we were doing it ourselves. Here's an octagon. You don't have to draw this if you don't want to. Just follow along. Okay, so if I start from, say, this corner, I would need 1, 2, 3, 4. Oh, that's a terrible one. Let me try that one again. 4, 5, and then I'm done, right? Because I don't need to hit this corner. It's already got 2 lines. So there's 5 from that corner. Notice this corner doesn't share any with that corner. Well, it already shares a line, but they're consecutive, so they don't have a diagonal to each other. So there'd be 5 at this one, too. Let's try them again here. That'd be 1, 2, 3, 4, and which one am I missing? Oh, over here. Missed this one. 5. Thank you. Will the next one be 5? Let me use a different color. I'll use purple. Will the next one be 5? No. What's it going to be? It's going to be 4. How come 4? Because there's already a diagonal here. This guy already exists. So it'll be 1, 2, 3, 4. Does that mean the next one's going to be 4? No. Let's use a different color again. Let's use green. That one's going to be 3. Because again, I've already connected to those two. I don't have to connect to this one. I don't have to connect to that one. So it really just leaves 1, 2, 3. What do you think the next one's going to be? How many diagonals do I have to draw from here? It's going to be 2. Because again, we already have connections to that one, that one, that one. Don't need to connect to this one or this one. So it's 1, 2. Which means that at this diagonal, let me use one more color. Let's see, do I have a blue or something? There we go, blue. I'm only going to need 1. There it is. And then the last 2, I don't need any. Because notice, every single other corner, there is only 8 corners, and 2 of them I don't have to put any lines to because they're consecutive. So 7 minus 2 is 5. 1, 2, 3, 4, 5. So don't need any there, don't need any there. Add them up. 5, 10, 14, 17, 19, 20. 20 diagonals. I think I did a pretty good job of that. It might not be quite as pretty as the one in your book, but did the job. That was kind of tedious, though, wasn't it? Actually having to draw 20 diagonals. Thank goodness it wasn't a bigger shape with more sides. So there must be an easier, I'm selling you something on late night TV. There must be a simpler way. There is. There's a formula. It's not slap chop. It's the number of diagonals formula, and it's a nice little formula. Notice that when I was doing the pentagon, I started with 2's, and 2 is 2 less, or sorry, let me say that again. 2 is 3 less than the number of sides, which is 5, right? Pentagon has 5 sides. And notice for the one that I was playing with the octagon, 5 is 3 less than 8. So minus 3 is kind of an important thing when you're counting diagonals. And that's kind of the main feature of the formula. Number of sides minus 3, then take that number and times it by the number of sides again, and divide by 2. Let's double check that that formula works. Let's try it on the octagon. So the number of diagonals, I'll use D for diagonals, is n, which is number of sides, times the number of sides minus 3 divided by, and I've already forgot. Oh yeah, divided by 2. Well, let's see. That's 8 times 5 divided by 2, which is 40 divided by 2. Yep, that's what we got when we counted, and that's what the picture told us. So yep, it works. Our formula works. Yay, let's do it on a simpler one. Use the formula to determine the total number in the pentagon. We counted 5. According to our formula, which is n times n minus 2 divided by, n times n minus 3 divided by 2, that will be 5 times 5 minus 3 divided by 2. 5 minus 3 is 2, so 2 divided by 2, here, I'll write it out, is just 5, which is what we counted when we drew our pentagram and summoned a demon. Okay, any questions on how that little formula works? It's a nice little formula. Let's try it on something bigger. Find the number of diagonals in a regular decagon. Ah, here's where you have to have that memory info. What's a decagon again? 10. So number of sides is 10. So the number of diagonals is 10 times 10 minus 3 divided by 2. And number of diagonals then is 10 times 7 divided by 2. And can I point out to you that you probably remember this already. Back in grade 7, you don't have to write this down. Some people called it bedmass, but you could also call it BEMDAS if you want. How come? Because divide and multiply don't have an order. You just do them from left to right. And this is kind of a stack. It's not really a left or a right. So if you like, instead of going 70 divided by 2, which is a big number, you could do 10 divided by 2 first, which is 5. So D is 35. There should be 35 diagonals. I don't know about you, but I'm still not 100% sold on this formula. Let's draw them. There we go. Let's draw them. Ready? There's my decagon. So I'm going to start from this corner here. How many diagonals should I be drawing? Again, you probably don't have to actually count them by drawing. You should think about it reasonably. There is 9 other corners. I don't have to put a diagonal to this one or this one, so I know it's got to be 7, right? So let's try it. So 1, 2, 3, 4, 5, it's almost curved, sorry, 6, 7. Yep. How many should this one have if I keep going around? Well, shouldn't it also have 7? Because it basically behaves the same as this one. And, I don't draw a line from that way or that way. So it has to be 7 again. So it's going to be 7 of this one, too. So 1, 2, 3, 4, 5. Oh, that's a terrible one. I'm going to undo that one. 5, 6. Did I count that right? Oh, yeah, I missed over here. 7. There we go. Now, logically, how many should this one have? It should have 6, right? Because I don't need to connect it over here, but there's still 6 more. 1, 2, 3, 4, 5, 6. And then how many should this one have? I'll do this one in red. Should be 5, shouldn't it? Because it already has 2 of the 7, so it needs 5 more. So 1, 2, 3, 4, 5. Keep on trucking. What should the next one be? Should be 4. 1, 2, 3, 4. What should the next one be? I need more colors. Should be 3. 1, 2, 3. And what should the next one be? 2. 1, 2. And then logically, this one here should be 1. And then the last 2 shouldn't need any. So 7 plus 7 is 14, plus 6 is 20, plus 5 is 25, plus 4 is 29, plus 3 is 32, plus 2 is 34, plus 1, 35. Our formula worked. That's what we got, right? 35. Yay. I will not on the test make you draw 35 diagonals. But I will make you draw at least one shape's diagonals, but it'll be smaller than that. The dodecahedron, yeah, that'd be, how many would that be? Well, you could figure that out. Okay, so there we go. That's the story on diagonals. Now, we're going to kind of pick up where we left off yesterday. Yesterday, we learned how to find an interior angle. Today, central angles and then exterior angles. So first, central angles. Why would that not get any bigger? I don't know. There we go. Bigger, bigger, bigger. What is a central angle? Well, first of all, a central angle is the angle made. I have to write a lot here. I don't know why they gave us a small line. The angle made at the center, RE for center, like a proud Canadian, center of a regular polygon. Here, I'll put polygon over here. Haha. There we go. It's the angle made at the center of a regular polygon by any two adjacent vertices of the polygon. So in other words, this vertex is adjacent to that vertex. They will meet at center, and then that creates a central angle. So that's what a central angle is. This appears to be an octagon. So how many central angles do you think it should have? Well, it should have, we connect all these with straight, well, I said with straight lines, and then I drew that. Try that again. That's not much better. Pretend all those are straight lines, would you? How many central angles did I make? 8. Basically 1 to every vertex, right? So there's 8 central angles. If it's a regular polygon, they should all be the same. And notice that if you put all these angles together, angle, 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 what do you get? You get a circle. So it should be how many degrees if you added up all of them? It should be 360 because it's a full circle. So the measure of the central angle for one of them would be to take 360 degrees and divide by the number of sides, which is this formula here. So let's try that in example 7. Determine the central angle of this regular polygon. Well, I need to figure out how many sides it has first. Start counting. Put a dot so you don't end up counting the same side twice. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, there's your friend, the dodecahedron. No, sorry, dodecagon. Dodecahedron's a 3-dimensional shape. So that's the dodecagon. It has 12 sides. So the size of the central angle, I'll just put CA for central angle if you're okay with that, is 360 divided by n, and n in this case is 12. I don't think I need a calculator for that. 36 divided by 12 is 3. Put a 0 on it. They're all 30 degrees. Cool. All right, example 8. If a regular polygon has central angles of 18, how many sides does it have? So the formula, the central angle, is 360 divided by n. Notice this time, they tell us the central angle. And I've said to you a couple times already this course, there isn't much algebra in this course, but there is a little. How do you get that n if you know 360? Sometimes, if your algebra skills fail you, sometimes you can figure things out in math by making an easier problem. Like, for example, if you had, you don't have to write this down, but suppose you had 6 divided by 3 equals 2. You know that, right? So if you didn't know what this 3 was and it was an n, well, you know it has to be a 3. So just ask yourself, say, self, what do you do with a 6 and a 2 that'll give you a 3? Is it 6 times 2? No. Is it 6 plus 2? Is it 6 minus 2? No, it's 6 divided by 2. So how do you end up with a 6 divided by 2? Oops, I was trying to erase that. How do you end up with a 6 divided by 2? Well, the 2 and the n switch spots. Ooh, that looks a little bit like the way sine law worked, right? Things cross and multiply, they switch spots. So that's what's going to happen over here. The 18 and the n switch spots. And I don't need a calculator for that either. How many 18s go into 36? 2 of them. So that's 20. So that's a 20-sided figure. We didn't memorize the name for a 20-sided figure, but you know what? It does have one. I should have known this, too. I actually looked it up, and then when I looked it up, I went, oh, yeah, that's obvious. Well, it's obvious to me because, and I caught, how many people play Dungeons and Dragons? What's your icosahedron die go up to? 20. So that's what an icosagon is. It's a 20-sided regular polygon. And that's what we just figured out. So that's a 20-sided figure. In fact, I just brought one over. I think I did anyway. Where are you? There you are. 20-sided figure. And there we go. 20-sided figure. Come on. Go big. Okay, I'll use the mouse. There we go. Okay. So notice this is 18 degrees. And I could figure out that this is 162 a couple of ways. What's one way I could do it? Well, check it out. Remember back yesterday, we had a formula for how big one angle is in a regular polygon. What was that formula again? Flip back a couple pages. Oh yeah, it was the interior angle formula. It said size of an interior angle. Oops, apparently I can't spell interior today. Interior angle. And the formula was that you take 180 times n minus 2 and divide by n. So let's try that. 180 times 20 sides minus 2 divided by 20. I would have to go 180 times 18 divided by 20. I think I might use my calculator for that. But I actually already know what it's going to be. Actually, maybe I don't need a calculator for that. 20 goes into 180 9 times. No, am I right about that? 9 times? Yep. And then 9 times 18 is not that hard either. 9 times 18, what's 9 tens? 90. What's 9 eights? 72. What's 90 plus 72? Ta-da! Can anybody think of a different way I could have figured out how big these angles are? These interior angles? There is another way I could do it now. I have another tool in my toolbox. People are looking at me like, why would you try to find more than one way to solve a problem when you already know the answer? Well, that's kind of the fun part. That's the way math works. It's like that saying, right? If you treat every problem like it's, or no, sorry, how's the saying go? Oh yeah, if you only have a hammer in your toolbox, you'll treat every problem like it's a nail. You should have lots of tools in your toolbox. So 162 I got using the formula from yesterday, but now that I know this central angle is 18, can I point out to you what kind of triangle this is? Begins with an I. Isosceles. And what do we know about isosceles triangles? The angle at this corner and this corner have to be the same. So if this is 18 degrees here, 18 plus something, or how about this? How about I'll do it as a minus. And for some reason I'll do it in purple. 180 minus 18 is how much these two angles have, and if they're the same, divide it by 2. And if you do that, you're going to get 180 minus 18 would be 162 divided by 2 is 81. So that means that this angle here, from here to here, is 81 degrees. And the interior angle from there to there would be just 2 of them. Oops. Ah! I wrote that down wrong. Ta-da! Isn't that cool? So now we have multiple ways we can figure things out in these polygon shapes. Okay, we got one other thing we got to learn how to do in these polygon shapes. We have to learn how to handle exterior angles. So go back to the notes, and top of this page here, exterior angles. Okay, first of all, what is an exterior angle? Well, we kind of learned this yesterday. It's the angle that is supplementary to the interior angle. So it's an angle found by extending the straight line of any polygon, and then period, and then I'll add the sentence. The angle is outside of the polygon. And that makes sense when you think about the word exterior. You go to the hardware store and you see exterior paint. What does that mean? It means it's paint for the outside of your house, right? It's meant to handle the weathering and stuff, so it's a little more, got a few more chemicals added to it than the interior paint. You wouldn't want to paint the inside of your house with that. Be a little too many fumes. So now, if you think about this triangle here, I'll just redraw it. You don't have to redraw it. If you kind of keep that line going, the interior angle is this one, the exterior angle is that one. And what do we know about that exterior and interior angle? Well, together, they make a straight line, so they are supplementary to each other. When you add up the interior and exterior angles at a vertex, you get a straight line. So here's a vertex. Add the interior to the exterior, and you get 180 degrees. This part's fun. This isn't so easy to see on a triangle, but we could try it. You know what? Let's try it with a equilateral triangle. I think I could draw an equilateral triangle using my tools here. Hang on. This might fail, but I'll try it. Insert a shape. There we go. Dip that. That's not bad. That looks fairly equilateral. Let's pretend it's equilateral. There we go. Okay, so there's my equilateral triangle. If it's an equilateral triangle, all 3 of its angles are the same. So how big are they? Yeah, they'd have to be 60, right? Because 360s would add up to 180. So if it's 60 degrees there, 60 degrees there, and 60 degrees there, now let's make some exterior angles. So let's keep the line of this triangle going like that. So the 60 is the interior. How big is the exterior? What would you have to add to 60 to get to 180? So that's 120. Then let's keep going like that. Let's keep this line going. So now that one would also be 120. And let's keep this line going. So that one's 120. So if you took all 3 of those angles and added them up, you get 360. Is that a fluke? Is that just because that's the way triangles behave? Let's try a square. Oh, what am I drawing for? I can make a square, I think. Wasn't square in my shapes too? That's a rectangle. Let's try drawing it. See what happens. Can I make it a square? That's pretty squarish. We'll take it. All right, we know how big are the angles in a square. Those are all 90s. So if I extend lines, I'll extend that line. So there's my exterior angle there. That's 90. Get it? They have to be 90s, right? Because they add to 180. I'll extend this one. So that 90. I'll extend that one. So that's 90. And I'll extend that one. So that's 90. So if I take these 4 purple angles, what's 4 times 90? It's 360 again. Let's check it one more time. Ah, we got this guy ready to go. Let's use him. Our regular icosagon. So if I kept this line going, and then I kept that line going, and then I kept this line going, and then I kept this line going, how big are all these angles? Well, if it's 162 from here to here, it's 18 from there to there. Interesting that this is the same as that. Is that always going to be true? I'll leave that to you to think about. It's 18s for all the exterior angles. They're all 18s. How many exterior angles will there be? 20 times 18. What's 20 times 18? 2 18s is 36 with a 0. I think we have a rule. For any regular shape, they always add up to 360 if you added up all the exterior angles. So if I want to figure out an exterior angle, I just take 360 and divide by the number of sides. So there's our third formula today. Size of an exterior angle is 360 divided by n, and let's use it to do a couple of examples, and then you can try doing the work yourself. A regular polygon has an equal exterior angles of 72. Calculate the size of each interior angle. Okay, well, 180 minus 72 would be, I guess that would be how much? What's 180 minus 70? 108. So how many sides does that polygon have? Ooh, okay, so if the interior angles are 108, what's the interior angle formula again? Flip back, and the interior angle formula is for one of them, is the size of an interior angle, I'll say SI, is 180 times n minus 2 over n. And I just figured out that that number is 108 equals 180 times n minus 2 over n. This is the most algebraic thing we're going to get you to do in this whole course. So how are we going to do it? Well, let's see. I have an idea. How about we cross-multiply this n? So the most algebra in the whole course, and they give us the smallest amount of room to do it in. Sorry about that. But anyway, if I multiply both sides of the equation by n, or if, again, I think cross and multiply, just like we did, again, back in sine law. So that n is going to move up to there, so that's 108 times n equals 180 times n minus 2. Now what do we do? The step we're going to do is a piece of algebra you learned in grade 8. It's called the distributive property of algebra. What that means is we're going to multiply both of the things in that bracket by 180. So I have 108n on this side. I have 180n, and then 180 times negative 2 is negative 360. All right, now I need to collect my n's together. This is basically like grade 8, grade 9 algebra. I'm going to minus 180 from both sides. If you take 108 and you minus 180, here, I'll write it down. Oops. Don't forget that there's a negative on that 360. Now what happens? What's 108 minus 180? Well, it's going to be a negative. I think it's going to be negative 72, right? And then what's the last step? How do you get n by itself now? You divide both sides of the equation. Now, how do you know it's a divide? Well, because remember, algebra is always the opposite of what's happening to your variable. This variable is being multiplied by that number. How do I undo that? I divide by that number. So I'm going to divide both sides of this equation by 72. Sorry, negative 72. And you can use your calculator if you want. The negatives cancel. A negative divided by a negative is a positive, which is good, because how could a polygon have a negative number of sides? What kind of interdimensional nonsense would that be? Nope, I'm going to get 5. That's the toughest algebra you're going to see in this course. If you can handle that, any little algebra that pops up from here on out, you will ace. Is there another way I could have found that answer without doing all that algebra? Oh yeah. Again, I've got more than one tool in my toolbox. What did I find out? I found out that the exterior angles were 72. They gave me that. So the other way I could have done this question was to say that the exterior angle was 360 divided by n, and then cross-multiplied. And hey, look at that. That's basically the same calculation I had here. I don't really care which way you get it, as long as you figured out that it was a 5. Cool. All right, so that's the second, or example 9, I should say. Finally, example 10. Here's a regular hexagon. Isn't it nice? Find the measurement of one interior angle. Okay, well, there's a couple of ways I can do this. How about I find the exterior? How about I do B first? 360 divided by 6, right, because the hexagon has 6 sides, is 60. So the exterior angles are all 60s. So the interior angles are 180 minus 60. No fair, you did B before A. I didn't break no laws. It's okay to do that. Of course, I didn't have to do it that way. I could have gone back to this formula and did 180 times 6 minus 2 over 6. I'd have still got 120. So these are all 120s. And then determine the sum of all 6 exterior angles. That's kind of a trick question. But you can add it up if you want to. What's 6 times 60? 360. The sum of all exterior angles on any regular polygon will always be 360. And there we go. That's the last example in our notes booklet. We have one more assignment to do in our workbook. I said our workbook. There it is. Lesson 8's practice in the workbook. So you can work on that. And if anybody finishes this assignment, show me that you're finished, and I'll hand you the last hand-in for this unit. We will also hand in the whole booklet on test day on Friday so that I can give you a mark for the workbook too. Okay? So there we go. Maybe before we leave, there's one other thing I wanted to mention. Remember, if you weren't here, was it yesterday or Friday? I gave out a formula sheet. I think it was yesterday. I gave out a formula sheet yesterday. If you weren't here yesterday, you can get it. And you're, again, just like the last test, you're allowed to write anything you want on the back, or actually the formulas only take up half the page. You have a page and a half. You can write whatever you want. I had somebody this morning asking me, so I have to know all of the rules for all of these shapes? And I said, well, yeah. And I said, and you're allowed to bring in the sheet. And they said, okay, but we were talking about a parallelogram. What are all the things you have to know about a parallelogram? Well, you have to know that opposite sides are equal, opposite angles are equal, opposite sides are parallel, diagonals bisect each other. And the person looks at me and goes, well, I'm not going to fit, if I have to do that for all 6 of those shapes, I'm not going to fit all that writing on there. Well, then don't write it in words. Opposite sides are parallel. There, I said that. Opposite sides are congruent. There, I said that. Diagonals bisect each other. There. I said all those words without writing a whole bunch of words. Right? So that's kind of what I want to see your formula sheet look like when you bring it in on test day. Unless you really feel like writing a whole lot of words really small, fit them all on a page. You can do that if you like. But I think this is by far the superior way to do it. And of course, if you need a reminder, you could write that, yeah, that's a parallelogram. Right? Oh, and you could put opposite angles are the same. There you go. Think of all the words you can save just by learning how the symbols work. All right, I just wanted to make that point. We'll call it a day there when it comes to notes and stuff. So you have the rest of this class to work on that, and if you finish it, I'll bring you the next hand-in assignment. Anybody watching this at home, thanks for watching.